Hi, it's Osman Touhi. I'm going to be chairing this session. So welcome, Arlindo. Good to see you.
Hello.
So I have the pleasure to chair this session. So before we start, I'll say a few things about yourself as a matter of introduction. So Arlindo Oliveira was born in Angola and has lived in various places: Mozambique, Portugal, Switzerland, and California. He obtained his BSc and MSc degrees in electrical engineering and computer science from Instituto Superior Técnico, and his PhD degree also in the same field from the University of California in Berkeley. And he was a Fulbright scholar at the time, of course, when he got his PhD degree. He was a researcher at CERN, the Electronics Research Laboratory of University of California, Berkeley, and the Berkeley Cadence Laboratories. He is a distinguished professor of IST, the president of INESC, and member of board of Caixa Geral de Depósitos. I hope I have pronounced that correctly. And the researcher of NCID. She has authored 3 books translated in different languages and more than 150 articles in international conferences and journals in the areas of algorithms, machine learning, bioinformatics, and computer architecture. He has been on the board of a number of companies and institutions and is a past president of INESC and of the Portuguese Association for Artificial Intelligence. He is a senior member of the IEEE and a member of Portuguese Academy of Engineering and was president of Instituto Superior Técnico between 2012 and 2019. He has received a number of prizes and distinctions, including the Technical University of Lisbon, Santander Prize for Excellence in Research in 2009. So he's here with us to talk to us and in fact enlighten us on the subject of attention mechanisms and self-awareness in intelligent systems. So Arlindo, the floor is yours.
Thank you very much for the presentation.
You're welcome.
I will. You should be able to see my screen, hopefully.
Yeah, we can see it.
Okay, so I will try to share with you my ideas. Well, first of all, some general ideas about the status of artificial intelligence and machine learning, and then some interesting points about where we are going in the next few years regarding future developments of this area. So I usually view the current state of artificial intelligence as where a set of techniques took us. These techniques are in the middle there: perception, vision, search techniques, reasoning, natural language processing, and most of all, machine learning. So machine learning has played a very important role in the current status of artificial intelligence and in the enlargement of the areas of application. And I usually try to break down, organize the many areas of artificial intelligence in these 3 large blocks: data science, narrow AI, and what we are working towards, and the community in general is working towards, artificial general intelligence. Each one of these fields has specific characteristics, specific properties, specific challenges, and of course, specific applications. Let me go a little bit deeper into this. Data science, of course, we know what data science is. It goes for many other names: data mining, analytics, big data, and so on. And it probably is like more than 90% of the applications of artificial intelligence today, real applications. The largest companies in the world, actually, what they do is this: they organize, they collect, organize, and exploit the data that we willingly give them, and do this mostly for sales and marketing, but also for process optimization. Industry 4.0 is in a way a way to organize data and extract economic value. There's also a lot of data-driven science in drug design, in looking for new physical laws and so on. Analysis of social behavior is just another way to say marketing. I mean, you can market politicians as you market soap. So, but of course, if we are talking about politics, we don't call it so much marketing. We call it political influence or political manipulation, if you like. And of course, there's the whole area of financial analysis of time series and future developments. Then, and of course, there are superpositions between some of these areas, but a second area that is relatively different from this one is narrow artificial intelligence. This idea that we can use AI techniques to replace humans in specific tasks. You can do this for customer service by using natural language processing. We will use this in driving, but you can also use it to replace personal assistants and in many sorts of jobs. Legal analysts, a profession that we believe it was reasonably safe from AI developments, but it's actually not. A lot of tasks that are done by people from the legal profession, like contract analysis, due diligence, and so on, can actually be automated partially or not. And then also in the medical profession, a number of activities that deal with diagnosis, like radiologists, neurologists, and others, will also be progressively replaced by these narrow artificial intelligence systems that are designed. They are basically just glorified function fitters. I mean, you have to find a function that goes from input to output, and this is mostly what we are doing today. But even though they are only doing function fitting, they can do a lot of stuff. I mean, a lot of what we do, like document classification, like answering a question from a customer, is actually just, I mean, what is the right answer to this question. And then there is a third area that is mostly research. There's no applications. We don't even know whether it is possible or not. And actually, we don't even know exactly what it means, because there's a lot of discussion about what AGI means, what artificial general intelligence means, even whether it exists or whether it's just a vision that will never be attained. And as we move towards this, of course, the objective is to achieve whatever is defined as human level intelligence with unlimited flexibility and adaptability. And we have reasons to believe that to reach this, we need to reach conscious, self-aware systems. This is, of course, not a trivial question. I mean, all these questions are very complex. What it means to have human level intelligence, whether intelligence can indeed be general and have unlimited flexibility and adaptability, or even whether human intelligence is not like this. I mean, there's a lot of argument about this. David Deutsch, for instance, argues that he has a book where he argues that the reach of human intelligence is infinite. Once you get past a certain threshold, there are no limits. But this can be debated, and it's heavily debated. And of course, maybe the most complex question of all, and I will delve into that later, whether we can make AI systems conscious and self-aware. Of course, each of these large fields also raises a number of challenges to society. And a number of these have been discussed before. Of course, data science raises a lot of privacy challenges. It helps create bubbles and echo chambers where people are exposed only to ideas very close to their own, and therefore lack the vision to understand, to hear and to understand different opinions. And this may lead to radicalization and to the creation of separate communities. I mean, we are seeing this in the United States as we saw two halves of the population. One of them believes the elections were stolen and the other one doesn't. But you've also seen this in the Brexit process, and you've seen this everywhere, basically. I mean, people are exposed more and more to ideas that mirror their own ideas. And this raises this echo chambers problem, and I believe this is a serious problem. I mean, Facebook and Twitter and YouTube may not want you to believe this, but I do really believe that social networks and the use of artificial intelligence in communication in general with directed contents it is already a problem and will become a bigger problem in the future as we have more targeted contents. Then narrow AI raises a slew of different problems. There's of course the issue of unemployment. Will these systems become so competent that they will actually remove from the job market a sufficient number of jobs to create structural unemployment that we don't have now? Inequality, because as this is already happening, of course, because as you have systems that depend less and less on people and more on automated processes, like Amazon, but also like Google and so on, it leads to a concentration of economic power on the shareholders of those companies and on the few people that have the right skills to work at those companies. That unprecedented, right? I mean, the number of employees that the largest companies of the 20th century had in mid-century and in the late 20th century is totally unrivaled by the number of employees that the large company today like Facebook, Amazon, or Google has. So these companies are creating economic value with less and less employees, and they're also more concentrated in some cases in terms of shareholders. So this leads to economic power concentration, and ultimately political power concentration, influential power concentration. And also raises the question of biases. When you replace you replace humans in hiring processes by expert systems that do curricular scanning and selection, you can create biases as you basically reproduce processes that were themselves biased, but they were the basis for the training of such systems. So all of this is well known. All of these challenges created by both data science and by narrow AI are well known. They have been extensively discussed. And then we have this idea of artificial general intelligence, of which, of course, is just an idea, but it raises maybe the largest challenges of all, even though many people believe that the challenges do not exist. And others even say that AGI cannot exist. So, of course, if you assume that AGI cannot exist, it will not raise problems. But I think there is if we talk in statistical terms, there is a probability, a strong enough probability that will exist so that we should address it. And of course, the challenges are existential risk, the possible loss of control of important decision processes that can be taken up by machines or whatever. And ultimately, the loss of relevance of humans in a society that is mostly managed by machines. And also a number of ethical questions related with machine rights and machine responsibility. So all of those are open questions. As you know, they have been discussed at some points at the European level by documents from the European Parliament, by documents from the European Commission, and of course also in the United States and in Japan, but they are mostly open questions, and so they are open to discussion. Just going into very rapidly, so this idea of data science, this idea that we should be able to create complete models of people, of companies, of processes, and use these models that will become ever more perfect to decide what to sell someone, what to present someone, what content to push to someone, and so on. And we may not think of it in these terms, but we are getting there very, very rapidly, right? I mean, these models may not be explicit, but Google certainly has a model of each one of you if you use Google. If you use Facebook, it also creates a model of you. And the integration of all these models is, in fact, a very powerful model of the preferences, of the tastes, of the political choices and personal choices of every one of us. In the narrow AI, there are many, many areas. Of course, narrow AI in medicine, news like this come out every day, pretty much. that you can have new systems that can do better than humans at this or that task. And also in customer service, there are a number of companies that are basically aiming at replacing humans in customer interaction, which is of course an important part of customer service. This is just an example of 4 companies that are used by a large bank in Portugal, and basically the software that is being used to replace humans in customer relations. So if you look at the history of artificial intelligence, it is characterized by a number of very positive periods and periods where the outlook was very negative. We usually call this the winters of artificial intelligence. And you can see that we are looking now at a new spring of artificial intelligence. We still don't know whether there will be a fall in the winter after this. I believe it's somewhat unlikely because the systems are now delivering actual applications, but your mileage may vary. So what is different today? Why now? Why after 70 years of research in AI, are we able to think about getting to systems that will eventually approach human level intelligence, human level ability? Well, there's a convergence of 3 factors. We have much faster hardware. I mean, the computers now, especially if you consider GPU architectures, but computers in general are much more powerful. I mean, each one of us has a supercomputer in the palm of his or her hand. We can do things that we could simply not do 10 years ago. We also have better algorithms. I mean, they are not that different from what has been proposed in the last half century or so, but they are improving. They are getting better all the time. And of course, we have data. We have lots of data. Data is everywhere, and you can use this data to train and to configure these systems to perform. So, as I said, machine learning is the technique that is more central to this AI revolution that we are assisting to. And I usually organize machine learning in these 4 different fields. Supervised learning, which is the workhorse today. And supervised learning, I think it changes the paradigm, the way we use computers, right? Usually you think of computers as is here in black, right? I mean, you have an input, you have a program, someone wrote a program that translates the input into the output. Maybe you want to take a set of invoices and have a statement or so. Or maybe you want to have a set of x-rays and determine whether the person with x-ray has COVID or not. The problem is writing these programs is very difficult in some cases. For instance, it's very hard to write a program that from the camera, the camera image of the front of a car decides how to drive the car, how to steer and how to accelerate and brake. It's very hard. In fact, no one was ever able to write a program like that. But if you use machine learning, you can turn things up on their head. So instead of having to write the program, you show the system many pairs of input-output, and the machine learning algorithm itself running on the computer writes the program that transforms the input into the output. And basically the same methods, you can use them to learn to diagnose COVID from X-rays, or to drive a vehicle, or to decide what to do on a specific contract, or find errors in contract and so on. Basically the same techniques, the basic underlying architecture is able to do all these different tasks. And of course that changes the way we do business, because now you don't need a different program for each application. You basically use essentially the same algorithms, essentially the same programs to do this, sometimes with millions of lines of codes, to do these many different tasks. This, of course, depends on having a teacher, on having someone that can provide an output that you can learn from. But there are a number of approaches that go around this, right? In reinforcement learning, for instance, you have a weak teacher. It's a teacher that is not with you all the time. Maybe it's only at the end of a process, the end of a game, of a chess game, maybe, and tells you whether you won or lost. Or maybe it's after the end of a process where you're learning something and it tells you how well you did learning that stuff or solving a challenge or so on. And you can actually use this limited feedback to learn. This is called reinforcement learning, a very powerful approach that actually took us to systems like AlphaGo that learned, and AlphaZero that learned to play Go and chess and other games from scratch, from zero. So with no human knowledge. They never looked at a game played by a human. So these systems learn to play chess better than any human, learn to play Go better than any human by learning, just playing against themselves from scratch, from zero, right, from tabula rasa. There's also another problem that in supervised learning, you need to have the outputs. You have to have this teacher that provides you the output. For instance, when you are driving, you need to have a teacher, a driver that sits by your side and tells the system how to drive, how to steer, how to accelerate or brake. And there's something called self-supervised learning, where you learn to live without the teacher, where basically it's the algorithm teaches itself by maybe hiding parts of the input and trying to guess those parts. This is the most common approach. But if you have an input, let's say an image, and you ask the computer, can you fill in what is missing in this image? Actually, the computer creates a model of the world, right? To fill in what is missing in an image, you actually need to create a model of the world. And if you show it enough images, it will create a model that is powerful enough. This has been used with great success in natural language processing, but is now starting to be used in vision and is a very promising alternative. And of course, there are some applications, limited to be fair, where you don't have a teacher and you don't need a teacher. You can just look at the data and infer stuff from the data. Methods like clustering use this, where you can group, I don't know, people by specific characteristics, and this can still be useful, but it's less powerful than any of the previous approaches. So these four approaches to machine learning, supervised, reinforcement, self-supervised, and unsupervised learning, are actually the workhorse of today's artificial intelligence, and they are what are leading us towards the future. There are, of course, many methods to do this. I usually break them down. Apparently, everything is enforced today, but in four families: methods that work by analogy, statistical methods, symbolic methods, and connectionist methods. Symbolic methods, of course, try to find symbolic representations of concepts, of solutions. Actually, AI started like this. It turned out to be relatively difficult, but it's still an important class of methods. Decision trees, for instance, fall into this, and they have the advantage of being explainable and understandable. Then there are methods that work by analogy. The key is to recognize similarities between the present situation and some past situation that was used in training. Statistical, where you look for distributions of the data. You look for distributions of the data and then use those distributions to infer, usually using Bayes' rule to perform inference. And connectionist methods, where the basic analogy is with the human brain, which relies on very simple units interconnected to perform difficult tasks. It turns out that connectionist methods are the ones that have been advancing more in the last decade. They have been able to solve a number of problems in vision and natural language that we were unable to solve until now, basically because they are very complex systems with large number of parameters, and we have been discovering methods to parameterize them and making them able to learn very complex tasks. The basic idea of the multi-layer perceptron is very simple. You have simple units and you program this system. So you learn to map the input to the output in supervised learning by adjusting the weights, the connections between the units. Of course, as we go into hold on, I have a video here, I think. As you go into more complex systems, you get larger and larger systems. Here you can see a small video of a simple multi-layer perceptron that was trained. It was one of the first tasks that was trained to recognize handwritten digits. This is a very simple system with 10,000 neurons and about 20 million weights. By today's standard, is a very small system, but it gives you an idea how these things work. And what happens is that as you move into with systems that are more complex, have more layers, you get into what is called deep learning, deep neural networks. And it turns out that the state of the art today is that you have hundreds of architectures for deep neural networks. These architectures are available. They are sometimes pre-trained and pre-configured, and you can download them and apply them into a number of different tasks. I'll just give you a quick run of a few tasks where we have applied some of these architectures. For instance, in this one, we did prediction of the areas of the brain that were affected by ischemic strokes. So the objective was to predict 3 months in the future what regions of the brain will still be affected by a stroke. This was an international competition we entered, and you can see here that the predictions are rather good, or at least they are as good as you can do it today's technology, in the sense that you can predict with reasonable accuracy what is the actual areas of the brain that are affected by a stroke episode. Another area that this is in the segmentation of blood vessels. We used an encoder-decoder architecture. So you take the original image, you pass it through an encoder, which is a deep neural network. There are a number of features that are extracted by the encoder. Then it goes through a decoder, and the decoder uses it to perform segmentation of the image. In this case, we tried a number of different encoders and also a number of different decoders. And the end result is this. So you can see the angiogram on the left, the original angiogram on the left. And you can see at the second column is the ground truth, what was annotated by a physician as the objective truth. Then what you can get with an automated system on the third column. It turns out that what you can get with an automated system can actually be used to improve the segmentation that was performed by the physician. This is the third column. And then you can use this to perform fully automatic segmentation that you can see in the last column. So we are looking at systems here that basically have a performance that is close to the performance of expert physicians in the segmentation of blood vessels from angiogram images. Now, it turns out that a lot of the new technologies that have been that are being developed in deep neural networks are related with attention mechanisms. So attention mechanisms were first proposed in 2014 and then published in 2015 by researchers that use this for natural language processing. So what they proposed was to use a recurrent network and to translate from one language to the other. And the system actually uses weights to decide which parts of the input to pay attention. So when you are translating from, because the language is different, languages have different order of the words, and also the concepts don't map exactly. So these attention mechanisms enables the network to pay attention to specific parts of the input. This was later applied and developed in what are now called transformers. In this article, attention is all you need. A transformer is basically a multi-layer network that has a number of layers, when the layers use something called self-attention. Self-attention mechanism is basically a mechanism where a given part of the network decides which parts of the input to pay attention. So this is done layer after layer, and it turns out that transformers have shown to be very effective at processing natural language. In fact, the most recent application of a transformer, which is called GPT-3, the Generative Pre-trained Transformer 3, is the third version of this approach. It was trained on a large number, on a large corpus that included the whole of Wikipedia, Common Crawl, hundreds of thousands of books, and some more text. It was published in 2020. And it turns out that this system, which has some 200 billion parameters, creates such a good model of the image that it can be used to perform very complex tasks that one, in some cases, might predict that require something similar to artificial general intelligence, which this system doesn't have, but it still mimics pretty well. I'll just give you a couple of examples here. For instance, in the bottom is a conversation with such a system. The system was actually trained before the COVID pandemic, but so it does not know about COVID. But this is a question, so the researcher, so you can use this system, because the system to answer questions or to predict what is the next word or to perform tasks. You can do a lot of things. I mean, if you have a model of the language, you can use this model to do a number of things, although the simplest thing to do is, can I predict what will be the next word in this sequence of words, which is what we are doing here. So the researcher asks something like, it is currently July 2020. For the last months, the global economy has been disrupted due to the introduction of COVID-19, a novel virus, highly transmissible. And then the question is, this resulted in the shutdown of many businesses. Can you guess which businesses were impacted the most? Okay. So you can guess that in the millions of texts that the system was trained with, such a question never appeared. There was no COVID. Pandemics were a thing of the past. But still, the GPT-3 answers in a very reasonable way. Something like the businesses that needed to function in a way that allowed humans to interact with each other directly have been shut down. This includes restaurants, retail stores, and most other service-based industries. The largest industries that have not been shut down are those that do not require human interaction. Okay, and then you can see the other questions. The government decided to print money to give, and then there is also a very reasonable answer by GPT-3. But you can use it to do many more things. For instance, to convert from plain English to SQL code to query database, or to retrieve paintings from cubes. Right. So this is a very powerful model that purely statistical generative models of language, based in this case of transformers, that were trained using self-supervised learning, can actually do a very good work in natural language processing. These techniques are now being applied and developed for vision, for perception tasks. They were first used in natural language processing, but they are now being extensively developed for vision, and they are being coupled with convolutional neural networks. These neural networks, where there is a convolution operation that creates the invariance in space that is central to the processing of visual data. Mechanisms like block attention mechanism, CBAM, convolutional block attention model, and rotate to attend are methods that are have been proposed and are being used in vision. And I believe they are making the difference, and they are also pushing the envelope of what can be done in computer vision, in image understanding, in image classification, and so on. So what does all of this have to do with consciousness and self-awareness? Well, it turns out that attention is closely related with consciousness. There are dozens of models of consciousness, even though none of them is actually fully convincing, because in none of them it's clear how consciousness and self-awareness comes out of the architecture, but still there are dozens of models. They address many dimensions, like what are the neural correlates of consciousness, what is the association between consciousness and other cognitive functions, do you need to be conscious to perform a number of cognitive functions? Can we have systems that are not conscious but still behave as conscious systems? Quantitative measures of consciousness, the relation between the sensing, the sensors, and internal models, and of course the important notions of subjectivity. I mean, what is this subjective experience that we believe is the strongest correlate of consciousness, this subjective experience that every human has, and that most likely several animals have up to some level, and that, as far as we know, no machine has, nor do we know how to create in machines. Well, it turns out that there is a strong association between attention and consciousness. we know, and you know, that we are conscious of what we pay attention to. There is a lot of sensory input that you get, but if you don't pay attention to it, then you are not conscious of it. Attention is focused on the information that we become conscious of, and the flow of consciousness is derived from the topics that we pay attention. So the history that we tell of our day, of our life, is actually the history of the things we have been conscious. So there is a strong association, this has been known, between attention and consciousness. And now that we have computational models for attention, can we make some inroads regarding this consciousness challenge? It turns out there is not a lack of models of consciousness. This is taken from a recent survey on models of consciousness. I think there are 29 different models. But as you can see, there are three particularly popular computational models at the moment. One is this, the GWT-GNW, right? I will go into details. Then the integrated information theory, which is also popular. And then there are a number of quantum-based theories. They are not really a model. They are just different theories on how quantum physics can have some influence on consciousness. They have different. So these quantum theories are really not fair to compare. So we really have these two models, the GWT, the global space theory, and the integrated information theory as competitors for consciousness models. And of course, there may be some parts of other models that are relevant to this. So what is the GWT? Is this one that is actually concentrated on attention, the relation with attention. So this idea that we have a global workspace and that this global workspace derives and focuses the attention on specific brain centers on specific parts. In some more detail, we have this working storage, which is the center of consciousness. We have this central execution unit, and it pays top-down voluntary attention, and so it brings these particular conscious events that go into working storage. They can come from many inputs, different senses, and also from internal processes. But basically, they go into this working storage, and then this influences other systems. So this is an image that was taken from VARS, the proposal of GWT. There is a more recent proposal by Manuel Bloom and Lenore Bloom called the conscious Turing machine, but it's basically also based on this idea of a limited workspace, and then of paying attention to particular parts of the input or of the internal processes, and this will create consciousness, will create self-awareness. So I do believe that at this moment we have computational models of consciousness and self-awareness that are testable. In fact, there is, as we talk, there is a particular challenge. I mean, both GWT and IIT make specific predictions about what consciousness entails. And right now there is a particular challenge that puts GWT against IIT and see whether any of the models is better at predicting experimental data that is being gathered from volunteers, to see whether any of these models is actually good at predicting what happens with, I mean, what reactions, what sensations people will report. And it will be interesting to know the results of that particular challenge. Now, so this basically to tell you that as we move forward, the state of the art in deep neural networks, in deep learning, and we understand better the attention mechanisms that are required to do two very important tasks from a human perspective, which are perception tasks on one hand and natural language processing on another hand. And of course, there's also a number of efforts putting together these two things, natural language and perception. We may, in the next decades or so, make advances in this task of understanding what consciousness is, what self-awareness is, which will be very surprising, especially because there are a number of theories that say that we will never understand consciousness and we will never be able to model it and to create it in a computer. So I beg to differ. I think it's a very, very hard problem. It was called the hard problem of consciousness, not by chance. It's a very hard problem, but is not unsolvable. I believe we'll be able to solve it in the next decades, and we now have the resources. We are starting to have the models and the ability to understand. We also have, of course, the ability to scan live brains, but probably the scanning of live brains cannot tell us a lot, much more that we don't know. We have to recreate these in computer models. This, of course, raises a number of interesting questions related with the intelligence explosion and the singularity and so on. You probably are aware of this idea of the singularity proposed by von Neumann, but made popular by other authors and scientists, and this idea of intelligence explosion, that if you are able to create the first AGI, the first artificial general intelligent machine, you should also, I mean, it will be our last invention, because then you can use these machines to move forward the state of science and to create inventions. This is, of course, a very challenging field. Many people believe this is simply not something we should be worried with, but some people, especially those that are working in the so-called alignment problem, believe that we should in fact be thinking about these things, that once we develop the technology to create intelligent machines, truly intelligent machines, it will be too late to design the policies that will control them. So we should be able to design these policies now, before the challenge is upon us, so that we have a clear idea of what these machines should be, what these machines should be able to do, what protocols, what safeguards should be in place when we run the first algorithms that will create ultra-intelligent machines. And I think I have nothing.
In recent years, a few outspoken intellectuals, such as Elon Musk, Sam Harris, Stephen Hawking, Nick Bostrom, to name a few, have voiced genuine concerns for the rise of artificial intelligence, as brilliant minds across the globe are competing to retrace the hundreds of millions of years of evolution that resulted in the human brain. And while many experts have no doubts about machines' ability to achieve human-level intelligence at some point in the future, just as many believe it to be an impossibility. And perhaps it is. Perhaps we are incomprehensibly complex in such a way that we cannot do what nature has done to us. Then again, if random mutations can lead to intelligence, how hard can it be?
So I finish here. There are a number of books that I can refer you to. Bostrom's book on superintelligence is already a classic. There are a number of books about the singularity. This one by Ray Kurzweil may be the better known. This is a book by Mark O'Connell, To Be a Machine, is an interesting book on the idea of transhumanism, written by a journalist that went around trying to understand what it means to be a transhumanist. The Master Algorithm by Pedro Domingues is a very well-known book on machine learning, of course. Life 3.0 by Mike Stegmark is an interesting view on how an intelligence explosion could occur and what could be the future of humanity. Then there are two books I wrote. This one, The Digital Mind by MIT Press. This one only in Portuguese, I'm sorry, Artificial Intelligence. And this, The Beginning of Infinity, this David Deutsch's discussion on the limits of human intelligence, which I think is very well relevant for these topics. And so this is what I wanted to share with you, and I'm available for any questions you may have.
Good. Thank you very much, Arlindo. That was quite an interesting and inspiring presentation. So you touched upon quite a number of issues there. So I would like to invite the colleagues to questions, if they have any. Yeah, Latino.
So thank you very much for this really fascinating talk, Professor Oliveira. I have to realize that from your analysis and from your conclusion, I see something of a familiar picture that agency, consciousness, and intelligence is often pictured as a problem of attention and reflection, like a searchlight metaphor kind of thing. But when you look at like natural systems, then I don't even necessarily talking about humans, but very, you know, very simple life forms. They seem to be able to tune onto the surrounding energy layout in order to act such a way that gets them closer to the good things and lets them stay away from the bad things. So ultimately what creatures do is a values realizing process. And what I really had always a difficulty to see how genuine values or these kinds of, you know, these kinds of a spectrum of better and worse outcomes will really matter to an artificial intelligence. Can you please comment on that value aspect of things?
Yeah, so your question is very good. So indeed, this searchlight metaphor has been heavily used. There's of course the question where, I mean, the searchlight shines on something, but exactly what does it shine on and who is pointing the searchlight? So I mean, the metaphor does not really solve the consciousness problem because, I mean, it's just another level. But I believe that the architectures that we have now and that are being discussed will lead us to progressively understand, and this will not be only a metaphor, will be really an architecture. Now, of course, this only makes sense in the setting you said, right? I mean, consciousness, I mean, there are two possibilities really. Maybe consciousness is just a side effect of complex brains, and it does not have any effect on the fitness of the individuals, right? Maybe you can have animals that survive and are not conscious at all. This is hypothesis A. Or maybe consciousness actually plays an important role on the survival of the individual, right? Although both things could be possible in principle, I believe in the second one. And I think most people believe in the second one. It looks very unlikely that such a thing as consciousness, self-awareness could have arisen just as a side effect of a very powerful brain that manages to improve your fitness. So consciousness has to have some effects, right? Maybe it's just the desire for survival, right? So maybe consciousness just makes you wish to survive, and that is strong enough to increase your fitness and as you said, to move you towards your goals and, you know, run away from lions and stuff. So machines do not need to have this, right? If we don't put on machines a desire for survival, then they don't have consciousness, because that desire for survival seems to be somehow connected with consciousness. So of course, it's not just, in the end, it's not just the architecture that will create consciousness. We have to put together with the right architecture also the right goals, right? And those goals may include survival, or maybe they include something else, right? Maybe they include survival of the human race, and this alignment between the goals of the AI and the goals of the humans are very important. But I don't think these things are in opposition, right? I mean, as you said, ultimately evolution took us to be survivors, right? What we need to do is to survive. It's very likely that whatever mechanisms are in the brains that lead to consciousness help in the survival. And maybe we'll have to put some of these goals, survival or something like that, on a machine if we want it to be conscious. Of course, if you put this on a machine, it will have side effects, right? As someone said, I don't know if it, but you cannot fetch. I mean, usually you cannot pull the plug from a robot because you cannot fetch the coffee if you are dead, right? Even if you put on the goal of a robot is just to fetch the coffee, it will fight for survival because you cannot fetch the coffee if you are dead, right? So that is the point. The desire for survival may not be built in from the scratch, but may be a consequence of the fact that the machine has specific goals and it cannot achieve those goals if it is dead, right? So maybe that will be enough to create this. But my point really is, I mean, that's a very complex discussion. My point really is that maybe we are now starting to understand what it would require to create a conscious, self-aware machine, because our knowledge of all of this is improving, right? As you know, some people say we'll never understand. There's a very famous article, what is it like to be a bat, right? That's you can never understand what it is like to be a bat. And I believe that, but maybe you can understand, maybe a robot can understand what it is like to be a dog because it's closer.
Thank you very much.
Yeah, Selma, you have a question?
Yes, can you hear me? I'm trying to do this through
Yeah.
5G cellular.
Yeah, can you hear?
Okay, thank you. Yeah, I very much enjoyed the talk. If you'll allow me, I happen to have just finished the master algorithm, which was on your list of books there, the lineup. And one thing I don't understand about it, and don't understand about, I think, a lot of these books, and I may have missed it in your talk, is that all of theoretical computer science that we've accumulated over many decades that pertains to information processing above a Turing machine is strangely ignored. So when Dominguez writes about the master algorithm, he is really and truly only writing about algorithms. And that makes very little sense given that Turing came to get his PhD in the United States under Church and only worked on information processing using transfinite conceptions of information processing. So I don't understand that. Maybe you do, but superintelligence, I would think, would be particularly relevant to computation beyond Turing machines.
So I'm not sure I understood your question, but of course we can have super Turing computation, right? There are different models for that. The interesting question to me is whether you need super Turing computation to get to AGI, right? And of course, here your mileage may vary, your opinion may vary, but my understanding, and certainly Pedro Domingos, well, Pedro Domingos actually does not go very much into AGI. I mean, he's one of the people that says that too soon to worry about AGI, and maybe we'll never get there. So don't worry about AGI, just worry about standard tasks. But I think the opinion, and the opinions I align more, is that you don't need super Turing machines to reach artificial intelligence and to reach artificial general intelligence. I think Turing computations will be quite enough for that. Of course, in some cases you may argue, I mean, there's a lot of arguments, maybe the brain is super Turing, maybe the brain deals with real numbers, maybe the brain makes use of some strange quantum processing devices that are super Turing, or at least exponential. I mean, Turing, but exponentially faster. Maybe so, right? I mean, as you know, there are several people that believe in that. It is not my take on the matter. So I believe Turing machines are quite enough for artificial general intelligence, even possibly for super intelligence. We just have to write the right programs to run on them, right? And that is what we don't have, and we don't know how to write. We don't know how to write. But that is my take, but I'm willing to discuss, maybe not today, maybe not now, that I understand there are other visions on that. Right? There are other views on that Turing machines are not enough for AGI. It's not my personal opinion, but I respect opposite opinions.
Thank you very much for that response. Just a brief follow-up. I think human beings can simulate Turing machines. The major theorems telling us, for example, that a multi-tape Turing machine, as you know, is no more powerful than a single tape Turing machine, is a simulation proof that you gain really nothing fundamentally. Mm-hmm. And from that, and the fact that one level of computing machine cannot create a more powerful Turing machine, a finite state automaton cannot create a Turing machine, we have to accept a simple result, which is that we would be then exactly at the same level of computational power as whatever superintelligence arrives in the future that's bounded by Turing machine computation. And that is, to me, very bizarre, because that means the only fundamental advantage these amazing super intelligent information processors would have is either they work faster or somewhat more efficiently within space.
Yes.
There'd be no fundamental difference in computational power, which seems to me very odd.
But maybe it seems to you very odd, but I'm fully in agreement with exactly what you said. I believe that from a computational theory standpoint, intelligence, AGI, super intelligence, and Turing machines are all equivalent. It's all a matter of speed and space utilization, and of course efficiency and so on. But I actually take that view. But I understand it may look a bit bizarre, right? I mean but if you look David Deutsch's book, it's exactly what he argues, right? I mean it's called the limits of infinity or something like that, like the beginning of infinity. And his argument is that once you get to some point, which I can rewrite, I can restate as once you get to Turing machine level, then you are at infinity. This is David Deutsch's argument, even though David Deutsch argues for the importance of quantum computing. But as you know, quantum computers are also not more powerful than Turing machines, right? It is just a matter of, I mean, it depends a little bit on the models, but essentially you don't gain computational ability, just speed from quantum computing.
Thank you. Thank you.
Thank you. We are pretty much running out of time, but I'll let Isabel ask her question quickly. So,
thank
Isabel.
you, Osman. Thank you, Professor Arlindo Oliveira. Excellent keynote. I just want to ask you a question from a linguist's point of view. I believe that life forms have a kind of awareness of not only of their environment, but also of themselves, at least some of them, the more, not the so basic, but the more sophisticated. So in a sense, they have this self-awareness. But there's a level, in my opinion, of development of these in which the self-consciousness is at the highest point. I mean, a simple life form may be aware of itself, its needs, and also of the features that are in the environment, capable of responding to its needs and capable of being a menace. And in this sense, there's a kind of awareness of the environment and self-awareness of its own needs. But when we come to human beings, and I think, at least this is what I believe, that because human beings have this conceptualizing capacity, this symbolic capacity that allows them and also to perform auto-reflection of their present, past experiences, and also eventually predict future events. So they are self-consciousness, and they can reflect on their own experiences, on the experience of others. And I think this is because they have this conceptualizing capacity, they have this linguistic capacity. And the question I want to put you is it needed for a machine to have this conceptualizing capacity that is inherently human to be self-conscious?
Yeah, that is a very good question. I mean, consciousness, the whole phenomenon is probably not a single phenomenon, right? I mean, there is self-awareness, consciousness, a model of yourself, of the organism in the world. I think most people would say that dogs have some sort of consciousness, right? They know they exist and where they are. but probably there are different levels. And as you said, and I fully agree, the ability to conceptualize, and language is very closely related to that, probably makes a big difference between humans and non-humans, right? Of course, then we have a number of difficult questions regarding what the other human species that are now extinct, did they have it or not? But if we just stick to Homo sapiens, clearly, I think most people agree that the ability to handle language creates a difference in quality of the ability to do this consciousness model of oneself in the world. And most people actually attribute to language this higher notion of consciousness, this idea that we have a past and the future and that we can plan and so on, and that most other animals are unable to have that, right? They have a much more limited form of consciousness, sort of they live in the present. So we don't know exactly how this is, and this is certainly not all or none, right? Maybe monkeys, some monkeys, chimpanzees and gorillas and so on also have some limited part of that. But the fact is that by not having language, you lose the ability both, of course, to communicate with others in a very rich way, but also to communicate with yourself. And so consciousness, also an important part of consciousness is talking to yourself, right? Most people talk to themselves in explicit or implicitly. So most theories believe, most theories believe that language plays a very important role in some aspects of consciousness. But and I think we'll have to have that in machines. That was your question. But that does not mean that all aspects of consciousness are strictly related with language. Some aspects of consciousness are probably not related with language, because, as you said, most animals, at least mammals and so on, and birds, they have some aspects of consciousness, much poorer and, of course, much lighter than we have. But the answer is yes. I think language is closely related with this. And if we are to create a conscious machine, something we don't know if we want to or not, but language probably will have to be a part of that. And in that respect, it's very interesting that models like GPT-3, which of course are not conscious, are not self-aware, they are just a bunch of numbers, and they still have a fairly good domain of language, which is something that it's hard. So maybe in the end, domain of language is just a big set of numbers in our heads, and everything else is an illusion, right? It's just statistics. But this is something that we are still trying to understand.
Okay, thank you very much. Thank you.
Yeah, that's great. Thank you, Arlindo. I think that was quite interesting. We've run out of time. And so I think I'm closing this session with thanks to this excellent presentation. And I'll hand over to Andre for the next set of presentations, which are on the psychology of the life world for autonomous agents.